Hello and welcome back to Differential Equations. Hello, all of those thousands of people that are tuning to watch this live. Uh, Today we are discussing again population models, and we'll talk a little bit about velocity and all that. And then I'm just gonna leave because it's no. The thousands of people that are in classroom right now are all excited. Two are smiling, which means we should start. In your previous calculus 1, 2, and so on, you've seen, and pre-calc as well, you've seen the most basic population model, the one where we said that the change in population in time is proportional to population, which when solved gives us population in time is equal to initial population e to the kt, where the k negative meant that population is decreasing, and k larger than 0, we have the population growth. Now, we also know that the graph for this equation looks like this. And we know that if we are to take the limit of p of t as time goes to infinity, is going to equal infinity, which is bad because we don't have infinite space on the planet. We don't have infinite resources. So this population model is good for the short run, right? Short term, if you have, I don't know, 10 years worth of data, you come up with the equation, right? You can extrapolate things that are close by to whatever you had that data. But overall, we know that this model has to be bad because it kind of just mushes everything into a constant k, the birth rates, the death rates, the exceptional death rates. So this model is clearly not good, and we would like to improve upon it and come up with better ones. And we start upgrading by realizing that the birth and death are not constant, right? So those functions depend on many factors, and in some cases, right, you'll have for, I don't know, first half of the year, country is okay, and then the second half of the year, and you're looking population of that country that particular year, second half of the year, war breaks out, right? A lot of people eliminated. So the death rate function would have increase on that case, in that case. So the first step of improving the model of population would be to introduce two different functions, beta of t, beta, Greek letter, b, right, stands for birth, and then death function, right, which is delta, again, lowercase d, equivalent for English. So what we get is that we're introducing beta, I call it birth function, and delta, death function. Because those are not constant, right? Even the birth function is not constant because it depends on situation in the country. A lot of people are lucky to start, 5-kid family if it's the Second World War, right, going around. So the birth function and the death function, both of those are really connected to whatever is happening. Right? There are a lot of factors that contribute to these. So now the difference between the two is what we are going to put instead of k, which was the constant growth. So we don't want the constant growth. because, as I said, situations change, and there is obviously impact. So now, the new formulation in terms of English language would be that the change in population is proportional to the difference of the birth and death functions, right? Multiplied into population again. So the change in population over time is equal to birth function minus the death function times p. It's also known as the general population equation, right? And when you average the entire planet, right, if the civil war or some small-scale war happens somewhere, on average the whole planet is not affected. But if the Second World War rolls around, obviously, right, or plagues in the past, right, that killed almost 2/3 of population. There we go, as an example. So clearly we have dp over p, and then equals to beta t minus delta t, everything dt. This is separable, and because it's separable, it's easy to solve. And now, once we are at the point where we understand that there is this difference between birth and death, we take a look and we keep realizing that the population of the planet is rising quickly, and it's actually rising at alarming pace, because some of the school of thoughts believe that the carrying capacity of our planet is even 10 billion. Some would say 15 billion. Because obviously it depends. I said it's not just the room where to build houses or where to stock people, it's also all the energy requirements, all of the food that needs to be produced and so on. So it's the maximum number of humans, let's say if we're talking about humans in this population model, it's the maximum amount of humans that the planet can withstand. And that's going to be called carrying capacity. So to go one step up and find this even better, we can work with what we call logistic equation. So logistic equations are going to be so here's an example. Maybe I can find, let me see if I can find a different example. No. Yeah, whatever. Logistic equation. So it's change in population in time. It's equal to 0.06p three zeros. It's over. I can't write zeros. All right, there it is. Finally. So what leads to this? I mean, what happens after this? Well, I hope you guys see that this is a separable equation, right? See that? So all we need to do is to move entire right side under the dt, and then bring dt to the other side, integrate both sides. Let's see what you get today. How do we solve this? What should we do? Partial fraction decomposition, yes, make it awful. I know. Good times. Instead working out partial fractions with 0.06 and 0.0. Let me see how much math you know from third grade. I'll give you a hint. Factor out 0.04. See what stays behind. And then shift it to the other side. Wake me up anytime. It's cozy. Is that good? And the answer is better be. So how do we integrate the left-hand side? Anyone? Come on. How do we integrate the left-hand side? Nope. I need p on top. If you want 150 minus p to be u, you have to have p on top, not on the bottom. It's not a basic integral. How do we integrate? Remember partial fraction decomposition? Yeah, you're gonna need it in chapter 4, so let's go. So partial fraction decomposition, a over p plus b over 150 minus b, p. Need to be equal to what? Right, so the scrolling is acting up, so we should just, I guess, quit. Yeah, I don't like this. So when we multiply, we get PB. We also have 158, and okay, this one is equal to 1, right? What do we do? Does anyone remember partial fraction decomposition at all? Nope. Do I need to write stuff on the board? I guess I do. I'm just gonna write the formulas. So when you have, that's invisible. Let's see, so So when you have something over x plus minus c, the setup is a over x plus minus c. When you have a repeated term, so you're going to need this for your repeated linear or inverse Laplace. You need it. And the only other one, there are four, like the repeated one, but usually never use it in differential equations. Something like that, or I need parentheses. The microfiber core. There we go. That's the setup. So we have two of these. So we go 158 minus AP plus dP is equal to 1 over that thing. Now what? And in the book, they don't tell you anything about it. They just say use partial fractions because you all passed Calc 2 and they know you know it, right? It's given. So now you have this situation, and you have the variables. P's are variables. So when you put P's together, right, they have to equal something with a P which is 0. And oh, this is 1. The constant term 150A is equal to 1. And B minus A, the hell I wrote that, equal to 1. And B minus A is equal to 0. How much is B? How much is B? That should not be a too hard question. What? It's the same as A. So now what you got is the ability to integrate the left hand side. So integral of one over, and you have P 150 minus P. Actually, wait. I need this in exploded form, which is this one when you put the integral in front. So A over P You're waiting for me to solve this, right? Because no one remembers partial fractions. You have your A, you have your B, you plug them in. So A, 1 over 150 divided by P, dP, plus the integral of 1 over 150 divided by 150 minus P, dP. So everything came from here, right there. We calculated A and B. So now, the first one is 1 over 150 ln absolute P, plus the second one is 1 over 150. And now, how do we integrate this? What do you mean the same thing? We have a negative in front of P. Have a negative in front of P. All right, so here, I'll copy it one more time so you can stare at it. What's the way to do this? Someone better know it. I'm going to update, downgrade all the grades from before. U sub, basic U sub, thank you. That's all it is, U sub. So we have 1 over 150 ln of P plus 1 over 150, and then the U sub here, so it's going to be ln of negative ln. Oh no, 0. What do I get? When I plug in this, I'm going to get U will be in denominator, so it's ln of 150 minus P. So that's all left hand side equals to 0.04 304P. Which DT? Where? Oh, I didn't write the DT. Yes, when it's separate variables, you must write DT. Thank you. Well, now we know who's paying attention. I was just testing. All right, so you have this. So multiply both sides by 150 and combine ln. It's algebra. Lots of fun. Oh, I wrote. Yeah, there's no P over here, just DT. Because that's the P is moved right there. What happened?
So we need, at the very bottom of the new line, it needs to be integral of 0.004, right?
Yeah, and that's where we pick up P plus C. So now all we need to do is to solve this and get P by itself. What now? Multiply through by 150. We have ln P minus ln of 150 minus P equals to what? The other number, 06. 0.06, right? Yep, 0.06. That's what we get when you multiply the decimal number by yeah. So you multiply this one by 150 through, get 0.6, and then you have your P plus till C, 150C, that doesn't change. You put the ln's together, which is P over 150 minus P, equals to 0.06 P, 1313, plus C. Exponentiate both sides. P over 150 P is equal to E 0.06 P plus C. Yeah, the pen is... All right, thank you. So now we just separate E to the P. Yeah, it's not ending up. I'm trying to process all of this parallel. There is something that I missed. Ah, the separator variables, it's dt. I hate writing things partially and then I miss it. All right, so guys, there it is. Finally, I can fix it. So I'll get off the charger for a second. Here was the issue. I'm trying to compute this over and over and over in my head while I'm doing this because it's not ending up. So we do separation of variables here. P and this one goes and just number stays. And then this T travels to the other side. Now I did have that as P earlier, and then I fixed it, but I forgot to fix it in integration. So I'm going crazy how to solve this. So the dt comes up. We do the partial fraction decomposition for the left side. That's all done correctly. And that's all left side here. And here's the integral for left-hand side. And we have over 150 and over 150. We're going to get rid of them, multiply through. But this is the integral that has to be t plus c. And this was tripping me off, so I still have to fix that. So now when you multiply through by 150, all the 150s go away. This is 0.06 T. Much better. So all we need to do now is to write this all as P equals everything else, and you achieve that by cross multiplying, breaking the terms, moving the P terms to the left, factoring the P out, and then so you get the logistics equation. Let's do that. Now that's going to be 3 seconds. So this is going to be equal to P equals to 150 e to the 0.06 t plus c, when I multiply that, minus p e 0.06 t plus c e to the, no, 150 times yeah, 150 times this gives me that, plus c. 150 was absorbed into c, so no one cares, and then 150, so that's done, And I need negative p, so negative p, and another negative cp. There we go. We move all the terms that have p to the left-hand side. Leaving 150 plus c on the right. Factor out p and divide by the whole thing. So factor out p. And then just divide. And there's a pt. And I think that in the textbook they use the wording as you can easily see, which is technically everything I did here. Okay. All right, so since there is so much stuff and mistakes, I'm just going to start from scratch, explain everything. So we are starting with the logistics equation. They give us 0.06p minus 0.0004 p squared. We factor out 0.04 p. We are left with 150 minus p, and then we integrate both sides. Now we have to do partial fraction decomposition on the left. Let me just put separation of variables because you know it's a differential equation class, so that's the most important part. We have the partial fraction decomposition. So we did that. We got 1 over 50, 1 over 50. And then we put 1 over 50 over p, whose integral is 1 over 50 ln p. Then we had the second one over here, again, b over whatever the term was. And we got this one from there. So now the first one is already done, nothing to do there. The second one is the one that we have to use u sub to get rid of the certain, like this negative p and so on. So what do I have? When I plug that in, so I have 150 over, and there's a negative 1. That's supposed to be a positive there? No coffee. That's supposed to be positive because when you integrate, right, you have a negative dp over here. So that's going to give us a negative up there, which is that negative over there. Oh, okay, that's fine. So 150, and then we multiply through, and we get this guy. All right, there we go. Cool. All right, so that's that. What else is there? So the carrying capacity is, you're going to get that when you take the limit of this equation. Carrying capacity is the maximum amount of rabbits that you can have in one habitat, or humans that live on a planet, or whatever. So carrying capacity is that horizontal line on our graph that that has to be obeyed as you are going towards infinity. So you let the time go for all eternity, and then you will see that the population is going to settle around a certain number. So I think technically that's it. The worst case scenario, you take the limit. That's to check the validity of the population model. Now, for the most part, that's it. More applications of the logistic equation, limited environment situations, competition situation, joint population situation. They all just vary whether they put the constant or not. And then you have a whole bunch of words to try for homework and see. So, technically you can expect like one exam question from these word problems in 2 sections or whatever it is. All right, so we'll restart the stream for the second part, and then we're done.